Hello, I'm Andreas Zeller from CISPA, and this is a recording of my keynote at TAIC PART2020 on coding effective testing tools within minutes. If I say minutes, I actually mean minutes, because in 18 minutes, I'm going to show you how to build a simple function fuzzer, how to build a dynamic analysis for execution, how to build static analysis for code, how to integrate a constraint solver, and finally how to build a symbolic test generator that exercises all paths in a program. These are all prototypes in Python for a simple program. But still, let's go. Enjoy. Okay. So we're going to start with a rather simplistic program, which I think most of you know. And this program that most of you know is actually called the triangle program. You know the triangle program? Shake your heads if you don't know the triangle program. It's a classic of testing. You can spend about 20 pages in a book just trying to properly test it. And I'm going to show you how this works. So this is a triangle program in Python. And if you go and I'm here in a Jupyter Notebook environment, so I can actually go and define things right away and also execute them. So I can find, oh, this is actually not a triangle. What am I doing? Let's do 1, 1, 1, and we should get an equilateral triangle. So what this code does is it takes the three lengths of the edges of a triangle and then characterizes this either as equilateral or isosceles or as scalene. Okay, and if you want to test this, well, you want to actually cover all these individual branches in your triangle program, which is actually not that super easy because you first have to figure out which values these three edges have to take. So, and just to get you acquainted with things, we're going to start with a simple exercise. I'm going to fuzz this thing, and in order to fuzz this, we need random numbers. So I'm importing a package here that gives me random numbers. The function randRange gives me a random number within a certain range from 0 to the number I give. So let's go. I can execute this multiple times, and every time I get another number. And I can now go and use this to actually create three random numbers. So here we have A, B, and C, and now I can invoke the triangle program with these three random numbers. Triangle A, B, C. Oh, well, what did I do wrong? Int object has, sorry, what am I doing wrong here? Range, so let me just, oh, so sorry. This is what happens when you type live. See, classic bug. And I can even show the results in here. So here we go. And I'm printing out whatever triangle gets us. And now we can see, okay, I've invoked triangle 10 times. And if I invoke it often enough, I will eventually also cover the, it will eventually cover the case where the three lines are equilateral. So there's nothing particular special about this, and this is not different in Python than in any other language. However, the place where Python shines is when it comes to dynamic program analysis. So in testing, in particular in test generation, you frequently need to understand what a piece of code is doing, during execution. And for this, you have to set up tracers, and these tracers are, well, can be very hard to build. If you want to dynamically trace a C program, for instance, this can be lots of work. You have to instrument the compiler and all. For Java programs, this is not easy either. In Python, it couldn't be easier. What you need in Python is you need a special function that is called a tracer function. We're going to get this in a second. And this tracing function is something that you can set up. This is trace it. This is something you can set up such that it is called at every line of the program. So every time a line of the program is executed, this trace it function is executed too. And the nice thing is you get information about plenty of things. So you can, for instance, access the current function code. You can access the name of the function. You can access the current line number. And you can even access all variables. That is the variables while the program is executing. And these actually come as Python objects. So everything remains Python objects. So there's no need to shift from one language domain to another. And what I can do now, I'm adding a couple of extra lines here to actually print these out, including the actual source line, which I also can get right from within the Python infrastructure. And this function in the end returns itself, such that it gets called again. Now I can go and actually call this thingy. There's an extra function called syssetTrace. This is this one, which actually enables tracing. And after we enable tracing, we call triangle. And then for every line in the program, in the triangle program, the traceit function will be called. And then we turn this off again. And if we now execute this function, that is triangle with traces, triangle traced. Here we go. What we get is an output. We get the name of the function, the current line, we get the source line, and we even get access to all variables while the program is executing. I have just built a debugger in about 12 lines of code. And well, okay, I copied this in now, but I could also have typed this in. This is something that takes minutes in Python, and getting access to all of this information using whatever programmatic device you do in whatever language, unless it's an interpreted language, is going to take you ages. And this is something where you would be 10 times, maybe 20 times more effective in Python than if you would do this in C, Java, or whatever you want to do. Now you can go and combine this, say you can combine this, since you now have access to the individual variables, and since you know which conditions are taken, and since you know which branches are taken too, you can now combine all this information, say, with your favorite fuzzer, and implement a search-based strategy that would evolve the population towards a particular goal, such as coverage. This is also a matter of minutes or hours at most. And then the nice thing is, once you have that, you can easily toy with your algorithm. You can fine-tune your algorithm. You can try out different alternatives without having to deal with a huge infrastructure first. So you can entirely focus on what your program is doing and what your program is doing, what your algorithm is doing, without having to deal with all of the difficulties of instrumenting programming languages like C or Java. This is also true for static analysis. If you want to do static analysis on, say, C programs or Java programs, you have to first deal with the huge static analysis tools, such as suit infrastructures that are simply gigantic, which are super powerful. That's certainly a given, but there is plenty of overhead which you need to deal with first. Static analysis in Python actually is, at least at the very basic, very simple. There's a package in Python which is called AST. And as the name already suggests, this gives you access to the abstract syntax tree of any code. You can actually go and first access the source code of some function. There you go. You have the source code in a variable, by the way. So you can go and triangle source. So here we go. You can go and show individual parts of this is the triangle source code as a string. You can now go and create, and you can actually now go and create an abstract syntax tree out of that source code, which actually at the same time parses it. And we can even have a look at this AST. There's also a package for that. Oops, and now with 3 lines of code, oops, what have I done? Show AST is not defined. Oh, okay, so sorry. From show AST, import show AST. See, here we go. And now we do have an entire abstract syntax tree, right, for us to inspect. And you can see that the triangle function consists of the function definition of triangle, followed by 3 arguments named A, B, and C. And there's an if, and there's another if. And eventually we return, say, equilateral as a value in the end. This is the entire syntax tree. Try that with another tool of your choice. And it certainly is not going to take you 3 lines or 2 minutes. Okay. And I can also go and search that tree. For instance, I can go and if I want to find out all the collections there, all the conditions there are in this tree, I can build a little list here that goes, and we're going to collect the conditions in here. I'm going to create a simple recursive traverse function, which traverses a particular subtree, and then it checks whether the node we are having is an if tree, is an if, and if it is an if, then if it is an if, what do? Oh yeah, we take the current condition, and for this, we actually transform back the subtree that is in the test of the condition. We transform it back into a string and save it in a condition. And then we go and append this to our set of conditions. Append cond. Here we go. Oops, sorry. Oh, this is to append cond. So here we go. Okay, conditions append cond. Here we go. And otherwise, we don't do anything particular. We just go and traverse the rest of the tree. So we go through all the children of the current node, and we go and traverse them. So this function actually now goes through the entire tree. If it finds an if, it's going to append the current condition as text to this array which we have here in conditions. Now all we need to do is we need to invoke the entire traverse function, and we return the conditions that we have found. Here we go. And this is something I can also we can now apply on our triangle AST. Here we go. And boom. And boom, we have just found all the conditions there are in our program. A equals B, B equals C, and A equals C again. You can compare that to the actual source code that we have over here. And you find that, yes, this is A equals B, and B equals C, B equals C, A equals C. Yes, we have all of them in here. And this, again, is something that is very easy to do, and you can very quickly do structural static analysis on a Python program just with a few lines of code. And then again, you can also transform these things. For instance, if you want to do mutation testing, you can go, I'm going to invert some of these, and I'm going to write the tree back. And again, this is a matter of minutes. And this is, again, something, build a mutation tool for Java, for instance. Yes, it's going to take you ages again. And now I'm going to show you how to actually make use of these conditions for testing. Because in Python, there is an interface for everything. And in particular, you can very easily get access, say, to the Z3 constraint solver by writing, hallelujah, import Z3. And Z3 is a tool that can happily take a number of symbolic variables. Here we go. We add A, B, and C as symbolic variables. And now I can create a solver from Z3, which looks like this. Now we have a solver. Solver doesn't do much. Now I can tell the solver a couple of constraints that I want to solve. So for instance, I want to make sure that all three variables, all A and B and C, have different values, which is what I need to have for a scalene triangle. And now I actually also need to say that these are not only integers, but these are actually also greater than 0. So I'm adding additional constraints in here. Here we go. And now I can actually check this whole thing, check whether there's a solution. And it turns out there is one. It's satisfiable. And I can now go and find out what possible values for these are. And I see that, oh, A equals 1, B equals 2, C equals 3. These are 3 values that satisfy these conditions up here. And this is now something, of course, I can now go and feed it into, I can now go and feed this into my triangle program and then test one of our conditions in here. So I'm converting these 3 values to integers, and I'm actually invoking it this way. Now, in order to actually make use of such a constraint solver, what we need is not only individual conditions, but actually path conditions. And here I'm now cheating a bit. I'm piping in a larger function that actually does traverse the tree and get us path conditions for all the if children. This now goes and builds a context and creates, and first builds a context, then it traverses the left hand of the if condition, then it traverses the else part, and for each of these it sets a context and actually creates a conjunction of the if condition, and such that everything that is in the if branch is actually executed under this, in this context. Which means that if we have something up here in this code, for instance, over here, A equals B, and here we have B equals C, this means that we now get the path condition A is equal to B and B is equal to C, whereas down here we have A is equal to B and B is not equal to C, because that's the condition we need to fulfill in order to get to that branch. Okay, I will leave this to you for further study. Here we go. And I can now go and create and collect all these path conditions, and which looks like this. And here are all our path conditions. These are the 5 conditions you need in order to get to the 5 branches of the triangle program. A has to be equal to B, and B has to be equal to C. Here we have the negation, and again we have a negation. And this is something we can now feed into our constraint solver. So all I need to do here is, for each of these path conditions, I create again a solver. I'm feeding in, well, the side condition that the 3 sides have to be greater than 0. I am invoking the solver check on this path condition. I'm using eval here because I need to turn these strings that we have over here into Z3 expressions again. And then I am getting a model. Here we go, which is a possible solution for these. And then I am actually invoking triangle on these values, and I print out the values beforehand. And what I get is now, for each of these 5 path conditions up here, I get a possible set of values, and I'm invoking triangle with each of these values. And you see that our 5 path conditions that we have extracted from the program before now actually return us the exact 5 paths, the exact 5 conditions as we have them in our program up here: equilateral, isosceles 3 times, and scalene. All of these are now being returned by solving these path conditions. So this is still very limited, okay? And as soon as you make any larger changes to the triangle program, you're going to need to make take a couple of more expansions. But what you can learn from this already is that in Python, which is what I want to push forward here, dynamic and static analysis are very easy to implement. You can come up with your own, and you can focus on your own algorithms rather than trying to figure out for weeks how to integrate Zoot or whatever infrastructure into your program. You have an enormous infrastructure that's very easy to use and to debug, for parsing, for handling program as trees, and for constraint solving. And this means that you can develop new algorithms in hours instead of weeks. So this was coding effective testing tools within minutes. If you're interested, under the URL, you're going to find more information about the code which I've been writing, and you will even be able to execute this all by yourself and try out things yourself. See you folks. Bye-bye.